Hey guys, we're back today, picking up in chapter 21 with confidence intervals for means, and today we're looking at the difference between two means. Now, this is particularly valuable because, the goal of statistics is to be able to make a comparison between two different things. Okay, so what we have been doing whether we're talking about a single proportion or a single mean, that was fairly limited in the scope of what we could conclude or what we could compare in those situations. But now, when we're comparing two different populations to each other, this is where statistics becomes very powerful. Okay, so again, we kind of led up to this in our previous section here, our previous lesson. It says to compare the population means under two conditions for two groups, we could construct separate confidence intervals for the two conditions and then compare them. That's what we did in our last section, comparing the weight loss for a diet-only group to the weight loss for the exercise-only group. We noticed that those two confidence intervals did not overlap each other. So the conclusion was if there's no overlap, then we see that there's no place where they could be the same. So that means that any differences that we observed between those sample means, that is a significant difference. What we're going to be doing today is looking at constructing a single confidence interval for the difference in the population means for the two groups and the conditions. Okay? We're still following the same general layout for a confidence interval, where we take that sample value and we're going plus or minus two of these, we're going to call them now measures of variability. Okay, that phrasing has changed from section to section. When we were looking at proportions, we still kind of referred to it as standard deviation. And the beginning part in this previous lesson, we referred to that as standard error of the mean. Now we have this new term, measure of variability, and I'll show you how we calculate that. So for performing this 95% confidence interval for the difference in two means, we're collecting large samples of observations independently. That is important, that you need to have independence between these two populations. Like when we're looking at the diet and the exercise groups, it would not be a valid comparison if we were selecting the two by like saying that this diet group, if you're not in the diet group, then you must be in the exercise only group, okay? So that they would be impacted by one another, okay? They have to be separately collected, they have to be independent. And you're calculating the mean and the standard deviation for each sample. Okay, so what's going to happen is we're going to have a couple different things. Actually, we're not going to be using mu because these are sample means. So we're going to have x bar 1 and we're going to have x bar 2 representing the two different population means. We're going to have a sample standard deviation 1, we're going to have a sample standard deviation 2, and we're going to have a sample size 1 and a sample size 2 for these two different samples that we're taking. We're going to calculate the standard error of the mean for each sample by dividing the sample standard deviation by the square root of the sample size. Okay, we remember that from our previous section. And then we're going to square the two standard errors and add them together and then take the square root. This gives us what we call the measure of variability. Okay, so all of this is in our equation sheet, which I have referred to but haven't shown you yet. It's linked in the top page of every one of our daily lessons. Okay, so this is our 19 to 21 equation sheet. Okay, you see some of the notation up there. We see the two rules: sample proportions, sample means, and then we can see standard error of the mean, measure of variability. We are looking at down here, this equation at the very bottom, confidence interval for the difference of two means. Okay, so you can see this is what we'll be building to today. We see the difference in these two sample means, x bar 2 minus x bar 1, plus or minus 2 of these measures of variability. we're going to expand on what that means. Um, to wrap up the week here, we'll be looking at calculator shortcuts in the next couple days. So at first, I want you to learn what these equations do, but we will be able to shortcut this using some of these calculator commands that you see off to the right. So to construct this confidence interval, we talked about this, this breakdown here. We see the two standard errors right there and right there. Each of those, again, is calculated by sample standard deviation over the square root of its own sample size. You're going to square each of those and then take the square root. This is essentially like you're finding a geometric mean of these two values. So let's go back to our diet and exercise example, and here's a refresher of what that sample data looked like. We see the two sample means for each group, we see the two sample standard deviations, sample sizes, and we calculate both of the standard errors right here so we can use these to move forward. Again, a lot of numbers to keep track of when you're comparing two different samples to each other. Next, we show the calculation of this measure of variability. So we take both of those standard errors, square them, add them together, take the square root. We get this measure of variability of about 0.81. And now the construction of the confidence interval. Again, this is called difference of two means. So rather than a single value at the center of the curve, we now have at the center of the curve the difference in those two sample means. So the center of that curve is going to be x bar 2 minus x bar 1. It really doesn't matter which one is which. Typically you do have the larger value minus the smaller value, but technically it could be small minus big if the order could be important. Recognizing that you get a negative value, and you're talking about a negative difference here. So it makes sense to have big minus small. When you work this out, 3.2 plus or minus 2 of those measures of variability becomes about 1.6. So our 3.2 goes at the center of the curve, and we have a step size of 1.6 going to the left, going to the right for each of these. And we can see here is our confidence interval in both kilograms and in pounds. Now, the big important thing is the interpretation of this confidence interval. Okay? Notice that both of these intervals, doesn't matter which units you're using, the intervals are entirely above zero. Okay? What you're interpreting from this is that if you have a difference that includes zero, then there's no difference between those two things. Okay, so if our interval ranged from, like, let's say negative 2 pounds to positive 3 pounds, okay, between diet and exercise, then you're saying, okay, a difference of negative 2 pounds could be a 2-pound difference from exercise to diet versus a 3-pound difference from diet to exercise, okay? And if there's a difference of 0, there is no difference between the two. However, because our interval is entirely above 0, that means that we have evidence that there is a significant difference, and we are 95% sure that that actual difference is between 3.5 pounds and 10.6 pounds. Okay, we are fairly confident, we are highly confident that there really is a population difference in the average weight loss, with a higher weight loss for the dieting alone than for the exercise alone. Now, a couple cautions about using this method. We talked about this at the beginning. This is valid only when you have independent measurements taken from the two groups. If you were to use some of this other design, like a match pair design, and one treatment is randomly assigned to one half and then the other to the other one, those are not independent. Okay, So that's kind of like what I said here with if you had a big group and then half of them were diet, half of them were exercise, that is not independent. Okay, they need to be separately drawn from different groups. In this case, the differences should be taken for each pair of measurements and then a confidence interval computed for the mean of those differences. So we have a couple examples here that I just want to go through and kind of emphasize the interpretations of their confidence intervals when you're looking at the difference of two means. So we're going to go back to a case study that we've talked about a lot this year. This is the mothers who smoke during their pregnancy and the subsequent function of the child a few years after birth. So particularly the subsequent IQ of the child. So in the research that these scientists did, they used 95% confidence intervals, almost all of them comparing the means for the mothers who didn't smoke and the mothers who smoked 10 or more cigarettes per day. We're just going to refer to them as the smokers. So first, let's look at the education level of the mother going into this. We see that we have two means here. We have two averages. The non-smokers, they had an average education level of 11.57 years. The smoking mothers, they had an average level of education of 10.89. So the construction of that 95% confidence interval, that difference was 0.67. If you were to subtract 11.57 minus 10.89, that's a difference of 0.67. You make a confidence interval and you get this value right here, 0.15 to 1.19. Okay, we are 95% confident that the actual difference in the maternal education was between 0.15 and 1.19 years. Okay, so the mothers who did not smoke are also likely to have more education than the mothers that did smoke. And this is a confounding variable. Okay, so you're kind of giving some credence to the confounding variables that seep into an observational study like this. Okay, there is a significant difference in the level of education of the mother going into the study. So any results that you see may not just be the cigarette smoking. Next is looking at the IQ of the children. Again, we see the two values up here. For the non-smokers, 113.28. For the smokers, the average IQ was 103.12. Okay, so there is that sample difference between those two numbers. Confidence interval, once again, 5.04 to 15.30. We are 95% sure that the actual difference in the IQs is between 5 and 15. So we have an interval that it is entirely above zero. We have evidence of a significant difference between these. The children of the non-smokers in the population probably have IQs that are between 5 and 15 points higher than the children of mothers who smoke 10 or more cigarettes per day. Lastly, we're looking at the birth weight of the children. The birth weight interval, again, we see the two sample means for the non-smokers and the smokers. We see the difference in grams between those two, 381 grams. So our 95% confidence interval, we are fairly certain that there is a difference, and that is between 167 grams and 594, almost 595 grams. Okay. So once again, we see a significant difference between these. This is an explanatory confounding variable. Smoking may have caused lower birth weights, which in turn may have caused lower IQs. Now, as kind of the overall results for this study, after control for confounding background variables, the average difference observed at 12 and 24 months comparing these two groups, was 2.59 IQ points. Okay? Here's our confidence interval for between 1 and 2 years old for that child after being born. Notice that that confidence interval drops across 0. Okay? However, as more time went on, between 36 and 48 months, so between the ages of 3 and 4, they saw that that difference in the IQ was now about 4.35 points. Now this confidence interval does consist entirely above 0. Okay, so you can't rule out the possibility that the differences in IQ were in the other direction at 1 and 2 years of age, because the interval does cross 0. At 3 and 4 years of age, the confidence interval tells us that the gap could have been slightly above 0 in the population. But you see that difference right there. I mean, you know that yes, it is technically above 0, but not by much. Okay, so be careful with any conclusions that you draw there. Okay. Last big thing about confidence intervals. We've talked about this a little bit before. We know that we use 95% confidence most of the time. We expect that 95% of all such intervals will actually cover the true population value. We expect error some of the time. 5% of the time, we expect it to not include that value. So, just like we saw with our probability, confidence in the procedure is over the long run. If you were to do a bunch of these confidence intervals over time, the same sample size over and over and over again, 95% of the time, they would be accurate. 5% of the time, they would be inaccurate. Now, if you wanted a higher level of confidence, okay, to be 99% confident, now think about the sacrifice that you're making. Okay? If 95% confident goes from here to here, well, to be more confident, you're going to be multiplying by a number bigger than 2. You're more than 2 standard deviations away. Okay? You're multiplying by 2.576. That's based off of the z-score chart. So you're saying that, well, I'm 99% confident. That sounds all good, but now you have a much wider gap. Okay, so if before you're 95% confident that your actual values between, let's say, 7 and 13, to be 99% confident, you're now saying that your values between 1 and, I don't know, 22, something like that, that sacrifice isn't always beneficial. Okay? If you were to lower the confidence, now you're only 90% confident, okay? You could narrow that interval. Okay, so now you're 90% confident. The multiplier here, you're about 1.645 standard deviations to the left and to the right. Okay, so your interval is now more narrow. Okay, typically 95% is a good compromise between those two, and that's why we usually see 95% confidence. Okay, but in certain cases, especially medical cases, test trials for new drugs, you'll want a higher level of confidence, so that's going to have a much wider margin.